So, is there any challenger there to give the opinion? Okay, Dewanga. Good.
Okay. My opinion. I think this is just some sort of abstract solution.
Yeah, that's fine.
Where I think first we must find the biggest number from the first array.
Yes.
Then goes to the second array. Maybe use some tree, or maybe just straight up find the biggest value of the second array. Then add the value.
Okay. Which value?
The biggest one.
The biggest one. Okay.
Biggest one at first. Then the third or next array. If the sum of the value is bigger than the money inputted, then backtracks a step to the second array or the array before that, then find the second smallest number, then goes to the
second biggest number, you mean?
Array. Sorry, sir?
You mean the second biggest number?
Second biggest number. Well, yes,
after you couldn't find like when the current state, for example, the third garment, the price is not sufficient, the money is not sufficient, then you return back the previous, right?
Yes.
And finding the second biggest, you mean like this, or you reverse it to the smallest?
To the second biggest, not the smallest yet. Okay. Not the smallest yet.
Okay. Go ahead, then continue.
And when it's already all of the array found the sum that is still smaller than the money.
Yes.
Will then show the sum of all the value.
Okay. I got it. Thank you for your. That's all, or do you have any maybe further observation?
I don't think I could make a tree or a tree of this.
Maybe you can share. Maybe you want to share your screen.
No. I don't draw anything.
Okay. Okay, that's good. Thank you, Dewanga. Let me put a point for you. Other participant? Maybe you want to share your opinion? Nothing to lose. Nothing? No? So, okay. If there is no further opinion, let us revisit the problem. So, actually what Dewanga proposed, what's the solution that Dewanga has proposed is, well, in general, we call this greedy. But it's not a common, well, it's not a common greedy, but like the modification style of greedy. Why? Because the solution, let me check over here. Well, this one. This is the general approach of greedy, which will result in wrong answer. Or it's possible also in Dewanga, it will result in wrong answer because we select from previous, and then whether it's wrong answer or time exit. One of greedy's idea is to take the most expensive model for each garment. So this is the biggest one, not the smallest one. The most expensive model for each garment that is still within the budget. In the example above, we can choose G0, for example, this one, G0, the most expensive price, which is 8. So we just select the expensive between 4, 6, and 8. So we select 8. Then we select 10. Then we select the remaining. We select 1 because it fits the rest of the budget, which is over here. And by doing this, we can apply it to cases A, B, and C. But what if? Let me modify. What if I modify the number of the value of budget, or this one, the budget, from 20 to 12, which is the same. Well, this is basically the same problem for all as test case B, but I just changed from 20 to 12. Based on the example, greedy technique will choose G0, 8, 12 minus 8, which is 4, and the system would give no solution because G1 G1 match the remaining budget, like 8 minus 8 plus 10 is more than 12, 8 plus 5 is more than 12, and based on the modification of Dewanga, then we can visit after we reach this one, we can visit the second biggest, which is 6 over here. 6. Then following, we can choose 5 because 10 is not eligible. Then after that, we can choose 1, which is, yes, it gives the answer. That's why it's like modification of greedy. It gives the answer, 6, 5, and 1. Then the result will be 12. Or the other solution is 4, 5, and 3, which is also 12. So with the general or common greedy, with the general algorithm of greedy, we'll get wrong answer. But with the modification of Dewanga, we may get correct answer, accepted. But the problem is we have to recompute it again. Like for example, in after we visit the first one, the second one, the third one, like what if there are like we arrive and at the last one, 20, and it's not sufficient. What do we what will we do? Well, we can revisit the previous, but maybe in the previous and the previous it's not enough. We have to revisit again. So it's we recalculate it again from the beginning, and that's why it makes the repetitive sub problem, which actually we can reduce it. Well, it's worth it. Worth try Dewanga. That's if we solve with Dewanga approach. And what if we solve with divide and conquer? Actually, well, this is wrong answer. This problem is not solvable using divide and conquer paradigm because the sub-problem are not independent. Actually, the requirement when we have to solve with divide and conquer is that the for each problem, well, for each sub-problem, it has to be independent within others. For example, merge sort. Merge sort, it's independent. If we revisit this one, merge sort. For example, 17, there is no relation with others. Whether 17 we put it over here or we put it over here at the beginning or we put it over here, there is it doesn't matter. So that's why it's independent and there is no relation. Whether we group it with 24, 31, 45, or we group it with others, there is no, there is no problem. But for Fibonacci, as you can see, there is a relation, which is this one is actually the value of A you can get from the previous and the second previous. And the value, the Fibonacci of 5, we can get from the previous and the second previous. The previous and the second previous, sorry, etc. So this one is dependent. That's why it couldn't be solved with divide and conquer. But sir, I saw a code, maybe they use divide and conquer paradigm. Yes, maybe, we will use this also. Maybe it's not literally a divide and conquer, but it's more like, wait, see. It's more like this one, which is complete search or recursive backtracking, which is in this case is backtrack brute force, and we can represent it like this. This is what, well, maybe If we use the way of Dewanga, we'll solve it like this. We represent it by 3, but the 3 for each garment, for each model. Each line represent, or each row represent garment. And for each garment, there are 20 models and the maximum possible value. If we visit this one, yes, this one, the optimal value from, well, the money from 1 until 200, and for C, the garment, there are 20, 1 from 20, and the price, no, sorry, for the price. For the K, which is the model, from 1 to 20. So if we represent the complexity, something like, it will be something like this. From 1 until 20, if, for example, this one is the most expensive, let's say we sort all the possible, all the price. So we start with the most expensive, and then revisit again. It's not sufficient. We move to the second, etc. And it's possible to visit until the 20. Then it's not possible. We have to modify the previous, etc. So theoretically, it's time limit exceed, but I don't know. It depends on the sample code or testing code of UFA. Why? Because it will be something like this. There are 20 garments, and the running time we have to check for each one. It's around to 20 until multiply with 20, etc. Then we can calculate. It's like 20 powered by 20. That's why it gives the time limit exceed. Well, it gives the correct answer, but there is time limit that we have to satisfy. We have to satisfy the time limit. And how we solve it? With we start with this one. This is non-dynamic programming technique, which is complete search or brute force, but with the approach of recursive backtracking. So we start with this one. It uses recursive. We start with the beginning, the input. If the money, like this one, maybe Mr. Subakti has explained that to solve dynamic programming, normally you have to define the set of the problem and the transition, which is the flow and what's the changing, well, the changing state for each sub-problem. If the money less than 0, then we return infinity, which is not possible. But if not, if G equal to C, return if the money is satisfied, well, if the money is satisfied, then return M minus money, the current money. If not, we have to revisit again and select the maximum answer between the answer and shop money. Well, the maximum option between this one and the previous one. So it's like, because it's recursive, it's we have to revisit again. Like when we have to find this one, we have to find between 1 until 19 the maximum answer, and then compare it by this one. If it gives maximum answer, then this is the new answer, and then return answer. This is how we solve with brute force, and it gives time limit exceed. Well, you can try if you are well. If you can try if you are curious. There is a source code also for this one. And the way how we solve it with dynamic programming, we can solve it with two approaches differently. The first one is top down. Second one is bottom up. So with top down, let us visit from this one. We have to determine the number of distinct problem. It means that the number of sub problem which is not which has to be calculated independently. There are 201 possible amounts of money because the limit is from 1 until 200, but there is possible that the money is 0. It means that if we have $20, we can spend until $20, which is 20 minus 20, which is 0. That's right, 201. Multiplied by the number of garments that we have to choose, which is 20, and 201 multiplied by 20 is 4,020. There are 4020 distinct problems. And we can use this as the maximum memory space we need. Okay, 4020. It's not that much, so it's fine. It's doable. For its distinct problem, it's necessary to calculate 20 models. The big O is K. So for its distinct problem, which means over here, it's possible to calculate 20 models. And because we have to combine all these things, like combine between this one, all distinct problem with the model, so we multiply, not plus, not power. We multiply 4020 multiplied by 20 models, and we got 80,400 operations per test case. Well, this is the total complexity, achievable less than 100,000. And how can we modify? After, like, for example, after we count this one, actually, the purpose of counting this one is to find out that we can solve it with dynamic programming. If not, we have to consider another solution, or we have to consider another approach. Another approach is we have to consider different representation, maybe not one of money, maybe not garment, maybe like different representation, and that's difficult. So the complexities, we have to calculate the draft complexity, and actually we can modify from the recursive backtracking from the previous source code from linear search with force by adding this one memo. As you can see over here, we have to save the distinct problem. Well, because it's distinct, we have to save all distinct problem. So we put over here, it's similar to this previous code. Even the flowchart is similar also. And we add after this one, if the G is not equal to C, then before we consider its, or we find out its sub-problem, we have to check whether this sub-problem has been solved previously. So we have to check over here. It's not -1, which is exists. Then return money. We don't have to calculate this one. So we can, for its distinct problem, we can optimize like 20 looping, 20 computation. So if there is it exists the sub-solution previously, we can revisit it again. But if not, we have to calculate it again. Same method and same approach, and then return the answer. Actually, when you return the answer, you have to save it to the memo. So after you count this one, you save the current answer to the memo. So you don't need to calculate again in the future. Well, seems complicated. And this is the source code. You can try, you can copy paste it and prove it, and it's yeah, it's accepted or not. Actually, this source code from Stephen and Felix Halim, top-down dynamic programming. As you can see over here, the differences between linear search and dynamic programming is these two lines, and the memo, this one, and if memo checking this one. Of course, this one, the third one. So 3 lines. Instead of, so we save the answer, the current answer in the memo, and then we return the answer. So that's all actually. Well, you can see over here there is memo. Well, you can. It's the additional. So if you delete these 3 lines, like you delete this one and you delete this one and you delete this one, just return ans. So it would be like linear search, recursive backtrack, and well, it gets correct answer, but it will be time limit exit. So that's top down. It's easy transformation from or natural transformation from recursive backtrack. Second approach is using bottom-up dynamic programming. Well, personally, I like this bottom-up dynamic programming because I like to imagine. Well, for me personally, it's easy to understand to imagine. Well, in recursive, you have to think in recursive way. The original form of dynamic programming. This is the original form of dynamic programming, and previously known as tabular method. Well, maybe Mr. Swakti has already explained it. So, what could we do? What can we do? We still consider the same state, which is money and G. 0 until 200, which is the 201, the size. And 0 until the number of G, which is the optimal possible is 20 or 21, because this one starting from 0. So how we calculate it? Oh, sorry, 0 until 19, sorry. Because 0, 1, 2 until 19. So as we can see, the maximum value is 20 and 3. In this case, we can create an array size of the maximum, like 201 and 20. But we can focus on the defined problem over here, which is 20. So we have to calculate from 0 until 20, just neglect others. From 0 to 20, firstly, we have to mark them all as false or f-1. Then we have to define the number of G as 3. So we don't need to consider 3, etc. until 19. And then how we do this is starting from 20 minus, you can see over here, the yellow one, minus 4. We put it as true over here, which is 16. 20 minus 4 is 16. 20 minus 6 is 14. And 20 minus 8 is 12. So this is how we start to solve, or this is how we imagine the solution. Then we continue to the following garment, which is this one, 5 and 10. So from this one, we can calculate if this one is not true, if this one is false, then we calculate it like 16 from this one, 16 minus 5, which is 11, or 16 minus 10, 16 from here minus 10, which is 6. So there is two possible over here. And then we do the same thing for 14 and 12. That's why there are two. And then we do the similar thing from the following garment until the end. So for this one minus 1, 11 minus 1 is 10, 11 minus 3 is 8, 11 minus 5 is this one, 6, I think, yeah. 6, 11 minus 5 is 6, etc. And as you can see over here, it's a redundant solution. It means that maybe we reach the same solution, recalculate the same solution, this point can be reached whether by this one or this one. And this is how we solve. Then this is the source code. Normally in bottom-up, it doesn't use recursive. It uses general, while, and for, etc. So iterative approach. Well, you can run this one, and we can continue. Actually, this is the source code. We'll upload it later. You can learn it. And actually, over here, because we can use, say, there is an optimization in dynamic programming bottom up, which is called space saving trick. What does it mean? It means that if we have, like, for example, if we have 20 garments, actually to find the optimal value, we don't need to save 20 possible garment. We just need to save the current row and the previous row. As you can see over here, previously, this one is from previous answer, and this one is from the previous. So we just consider 2 lines. The requirement for this one is if you are asked to solve to give the optimal solution, to give the optimal value. Sorry, not the optimal solution. So instead of saving reachable, like saving the memorization 20 and 201, we can use 2 and 201. Such an optimal for the memory. Well, this is the differences between top-down and bottom-up. But before we go to the differences, is it clear for you, or is there any question? Maybe you still don't understand it yet. The differences mainly, well, not necessary specifically for this problem, but the differences between top-down and bottom-up. Maybe there is any question, because it's important, and if you want to work in the big company, normally they would like us to something like there is a programming review or programming interview, and they would like to ask this kind of question. No? Okay. If there is no question, this is the top-down and bottom-up, the differences. The good thing about top-down is then it's natural transformation from complete search regression, and only calculate the subproblem if needed. While in bottom-up, we have to, if there are M states, all values of for M state will be visited and filled. It means that we have to calculate all subproblem. While in bottom-up, the pros, and the good thing is the computation time required to visit the subproblem is faster because there are no recursive calls. Actually, this is the basic knowledge for you that if you use recursion, the computation time is if you use recursion, it's higher. The computation time is higher than if you only use like for or iterative approach. And second one, it can optimize memory space by the space saving trick technique, like I'm giving the example previously. And the cons or the negative side of top-down is slower if many subproblems are visited. Recursive calling effect. So it's recursive calling, the effect of recursive calling. You call recursive several times. The second, if there are M states, a debit table of size big OM is required because memory limit exceed. So there is a state. This one we can, well, in bottom up we can optimize with this one, but in top down there is maybe if the value of states or distinct problem are larger than expected, it may cause memory limit exceed. But rarely happen, I think. Except for maybe for the competitive programming with strict requirement. And while for the negative effect of bottom up is this one is not suitable for programmers who are familiar with recursive style. Maybe you are more familiar with recursive style. And if there are M states, you have to fill out all the states, and it affects the computation time. As you can see over here, it's pre-compute. You have to compute all the possible solutions. And how to solve, how to show the optimal solution given the previous source code. If we use a bottom up, we can do something like this, reachable this one, and then we revisit it again. This one we get from 1, something minus 1, which is we add by 1, this one. And then this one we can get from something minus 10 to 10. So we add this one by 10, which is this one. So we can get the one optimal solution. 1, 2, 3. This is how you get the optimal solution. Or you can do another thing starting from here. after 1, we can try with 3, and we can try with 5. And then after that, we can try 3 with 5 or with 10. Then this one with 5 with 5. Actually, it's not possible over here. So actually, this one with 10. Well, yes, with 10, and then this is 4 extra. That's how you get the optimal solution. And for the top down, you just need to add this one, printf percentage G percentage C, or save in the in another array, so to save the optimal solution. And I think this is from the course of Mr. Subakti. That's all how we solve the dynamic programming in top down or bottom up. Well, this is actually it's been explained with Mr. Subakti. And this is important. Actually, why we need to understand the paradigm, the purpose, one of the main purpose is that not all of us are gifted. Well, even I'm not expert in design and analysis of algorithm, but by understanding the category over here, we can do the similar approach. For example, in this one, max 2-dimensional range sums, you can, for example, you do this one. After that, you can modify this code to solve this one, and then you can modify this one also to solve this one. Maybe the differences is not as bigger as you use this code to this one. Maybe it's not related. You have to rethinking again, rethinking the new solution again. But if it lies in the same category, you can solve it in the similar way. Just currently, well, there are more than 6. There are max 1-dimension range sum, 2-dimension, longest increasing subsequent. There are also longest LCS, longest common subsequent. I think Mr. Subakti has explained it for the LCS, common subsequent, string, etc. There is 0-1 knapsack. Well, there is 0-1 knapsack and partial knapsack. Well, we will try to solve it. Next, there is coin chains. The last one is there is traveling salesman problem. Actually, there is another thing also which is called cutting road. I think, yeah, cutting road, etc. And this one is non-classical. What does it mean? Actually, the categorization of this classical and non-classical is evolving, and it's dynamic. So maybe in the future, next 5 years, there is a new category in classical, and well, or there is a new category for or for non-classical, there is some modification. For example, the previous code that I show you is non-classical because, it's not literally, or it's not similar to one of these 6 category. That's why we have to think it differently. But this is good as an example. So, okay. Is there any problem so far for understanding? I think there is no problem. If there is no problem, well, this will be your assignment. So never, don't worry. You just need to select one. Just only select one problem, not one for each category, only one. But before we go there, we go to this problem. I want to show you how we solve it with, well, this is my, so far, this is my current best practice to solve the problem if we are not gifted with the special gift of special ability to understand dynamic programming or competitive programming. Let us visit this problem. This is in Bahasa. Is there any difficulties for understanding Bahasa in this class? No, okay, that's good. So try to visit this problem. will explain. It's called it's dynamic programming, uang kembalian. So as you can see over here, it's in the same category as this one, coin change. So you can solve it by maybe if you have already solved this one or this one or this one, it's easier to solve this one. You can reproduce the code. So let us read the code. Let us read the description. Koin kembalian adalah persoalan yang umum ditemukan di mana-mana. Saat Anda bayar belanjaan, jika uang Anda tidak pas, tentu Anda mengharapkan uang kembalian. Dan secara umum, kita mengharapkan uang kembalian dengan koin yang sesedikit mungkin, supaya kantongnya tidak menjadi berat. Anda diminta untuk menuliskan sebuah program yang dapat mencari kemungkinan kembalian dengan banyak koin sesedikit mungkin. Let's say this is the cashier of Indomaret, and and then you cashier asks you to solve to give the recommendation, which is to give if you need to return like a certain value, how many the smallest possible option coin that you have to giving to the customer. The first row over here, baris pertama berisi bilangan n, nyatakan banyak jenis koin. This is the number of the coin, 4. And the second line is the currency of each coin, the value of each coin. Sorry, not currency. The value of each coin, 1, 2, 5, and 6. And the last one is the K, which is the coin change, and the money that you have to return, or you have to represent it with this coin. And the output is 2. The number of coin minimal yang dapat digunakan that you can use to represent 10 over here. For example, 2 comes from 2 coin of 5, which is 10. This is the optimal. If we can use like 6, 2, and 2, but it's 3 coin. Or you can use 2 and 2 and 5 coins of 2, but it's not the minimals or the minimum value. That's why the most optimal solution is the most optimal solution is 2 coin of 5. But if you couldn't, jika Anda tidak bisa menyatakan kembalian, if you couldn't represent this one as these following coins, you can return -1. Maybe if we delete 1 and we want to represent 9, it's not possible because 2 plus 6 is 8, but 2 coin of 2. Oh, okay. Sorry. For 9, we can do with this one. Well, just delete 1 and 2. It's easier. So we couldn't represent 9 with these 2 coins. So that's why there is a -1. And for the limitation, the number of coin over here is between 1 until 500. 500. And then there is it's limitless, so there is no limitation stock of for each. For example, we can use like 5,532 coins of 5. Maybe if that's the most efficient way, it's possible. So there is no limit number of the coin. And the K, the value of K is between 1 until 50,000. So I'll give you 10 minutes to understand the problem and give like previously, like what Dewanga did, give how we can solve it, this problem. Ten minutes starting from now. Wait, is there any question before before you start to think about the solution about that problem? No, so I think it's clear. Okay, good. So, is there any gladiator want to try to solve the problem? Well, not literally the problem, but maybe give the opinion. Is there any? 29 students? Not Dewangga. Wait, let us wait for others. Come on, never mind is whether, well, it's correct or wrong, it's never mind. The most important that you try. So that you tried. No, nothing, no one. Let me check. There is any. Husnan, are you there? Check Husnan. Check. Husnan, check. Yeah, this is what I'm afraid. With the distant learning, that's well, you might be not in the course, not present in the course, or maybe we check others. Mutia Kurota Ayun, are you there? Mutia?
Yes, sir.
Yeah, can you help me to explain how can you solve the problem, maybe?
I still have no idea, sir.
Literally, or well, you can guess.
But I don't understand, sir.
Which part of the problem that you don't understand? Well, you can try. You can speak in bahasa if you want. Or mind. So Mutia, which side of the problem that you don't understand yet? Maybe I can re-explain it again. Nothing. Well, okay. Well, nothing. Okay. Thank you, Mutia. At least you try to speak up. Thank you. Let me check with others. Maybe Fuadil Hassan, are you there?
Yes, sir.
Can you maybe you can try how we can solve the problem of uang kembalian?
Sorry, sir. I don't know.
Okay. Okay, thank you for the speak up. Putu Ananda? Ivan. Okay, Ivan. Okay.
Tes. Oh,
Yes.
mungkin saya punya buku yang isinya itu menjelaskan problem ini, sir.
Exactly. That's good. Yeah. Yeah, that's what I want to explain also. Show us.
Can I share screen, sir?
Yes, you can share the screen.
Jadi yang pertama itu, ini problemnya agak sedikit mirip, tapi tapi jenis uang yang akan dikembalikan itu cuma koin 1, koin 6, dan koin 10. Terus yang diminta itu koin 12. Jadi yang pertama itu solusinya bikin 12 indeks kosong. Nah, setelah itu yang indeks 0 itu dikasih base case yaitu 0. Yang mana kalau 0 itu nggak perlu mengembalikan uang berapapun. Nah, kemudian selesaikan dengan cara bottom up, maju ke indeks 1. Nah, karena kita punya jenis koin yang bernilai 1, jadi kalau disuruh mengembalikan uang bernilai 1, kita punya 1 koin. 1. Nah, setelah itu lanjut ke indeks kedua. Nah, indeks kedua juga sama, karena kita punyanya koin jenis 1, 6, dan 10. Untuk indeks 2 juga memerlukan 2 jenis koin indeks 1 untuk 3, 4, 5. Nah, yang berbeda untuk koin 6. Karena koin 6 ini kita punya juga jenis koin 6, jadi ya daripada mengambil 6 jenis koin 1, mending mengambil 1 jenis koin 6. Kan kita juga punya koin jenis 6 juga. Terus untuk 7 juga sama, karena kita nggak punya koin 6 tambah 1, karena kita juga punya koin jenis 1. Kemudian untuk yang ke-8, karena kita nggak punya koin jenis 8, jadi ngambil dari 6. Kemudian karena 6 masih kurang, kita cek berapa sih kurangnya. Kurangnya 2. Nah, kita punya koin 2 apa enggak? Kalau ada berarti ambil aja 2-nya. Tapi kan kita nggak punya koin 2, berarti ngambil yang 1. Nah, setelah itu gitu terus sampai beda ke 10. Karena 10 punya, ya mulai lagi dari koin 10. Terus untuk yang indeks ke 11 dan 12 juga sama. Nah, I think that's it.
Okay, that's good. Thank you, Ivan. Yes, that's exactly that I want to explain to you. So, okay, you can close the screen. Sorry for others. Actually, my internet connection is not clear, I think. So, I want to stop my video, but let's discuss, continue to discuss. So that's yes. What just Ivan did is what I want to share. Why? Because not all of us can understand the problem directly, or can thinking the solution directly from the given the problem. So what is important is that you have to understand which category this problem lies. So, for example, given the question, given the problem like uang kembalian or coin change, so you can this one it lies in coin change, or maybe we can solve it with coin change approach. So that's why we can use this. And let me put the point to Ivan before we continue. Nabil, are you there? Nabil? Yeah. Usually you speak up, but I don't hear your voice today. So, okay, let me prepare the source code. Let me check. So, okay, let me share the screen. So this is the problem, and how I solve the problem is, let me check. Well, not allowed. As you can see, well, even for this problem, as you can see over here, I just tried. Well, when I prepared this course, I tried to solve it again with the different accounts. So as you can see, it's not directly accepted. Why? Because I tried to duplicate from this one, the same book as Ivan, as well as you can see over here in this TLX Toki. It provides a good book in Bahasa, not complete, but it's good to understand. Which is this one, coin change. So what I do, or what I did, is this one. So I select between top down or bottom up. So I prefer bottom up. Then I convert this pseudocode directly to the source code. That's why sometimes I get a wrong answer, runtime error. Runtime error, it's because of the, well, I'm not translate this properly. So once I translate this problem properly, this pseudocode properly, I get the correct answer. So this is, let me compare one by one over here. So what I did is this one, as you can see. Well, the most important is before you start to implement the problem, etc., just make sure that you can handle the input as well as the output. Well, the output comes later. You can handle the input. So after that, you handle the input, then make sure that the input is correctly saved in the memory. Then you call the function, which is this one, function solve. And in this one, well, in this case, I don't need to use this one. It marked all the possible or all the zeros. Wait, this is the correct answer or not? Yes, I think. But in here it used 2 dimension. Let me check with others, maybe my other submission for here. Oh, this one, I think it's the other submission. So, okay, I think it's easier to understand with this one. Let me copy all. Let me put over here. And let me activate this one. Control S, run the code. So this is the source code. 4, 1, 2, 5, 6, and we have 10. We have this one. Oh, I think because it's outside of 4. Let us print like this. Control S, run it again. 4, 1, 2, 5, 6. That's 10. Normally it gives corners. Oh. Well, as you can see over here, it's just like what Ivan explained through the book. firstly, we have to prepare the size. Well, in here, we go directly for here, because this one is the base case 1 and 2. Well, we can stop it. Actually, this is the base case. We can neglect it, so we can do it directly for here. We can neglect it for this one. I mean, this one is conscious, yes. So we start with giving the memory as the. Wait, I think there is a differences between this code. And mention this one. No, this one is conscious. So firstly, what we do is this one. Let me. So we flag. We flag over here. Firstly, the optimal solution, the best current solution is the previous solution. For example, in this case, to get this coin, we'll get the sum of this coin, or the number of this coin. For example, if for 1 over here, well, this one is 0, 1 until 10. This is 1, so we get 1 coin, and then 2 we have 1 coin. Actually, it's not directly with 2 over here, but it's 1 and 2 coin of 1. Then after that, if and this one replace, so we find the minimum value, and then we replace it by 1 coin of 2. If you want to prove, you can show it over here. Something you can print like something like this. Then just print to see the evolution of the value. For 1, 2, 5, 6, and 10. So for 1, there is no. This is for each iteration in here. So we calculate all for coin. Then starting from here, as you can see over here, the beginning, we set the maximum value. We set this maximum value, and then after that we change it with the minimum value of this one compared with the maximum 1 million to this one, which is the previous plus 1. The previous plus 1. So 1 plus 1, which is 2. That's because we just use coin of 1. Then after that we use coin of 2. So we can replace it compared with 2 and 1 over here. Then it gives 0. Well, it's 0 it's because the beginning, the memo is 0. 0 plus 1 is equal to 1. That's why I put over here. Normally, if you put in global, the initial value will be 0. Plus 1. So the minimum value is 1. Then that's all we get. Then it works also for the previews for the next, then etc. For this one, 3, because we can represent 1, 2, 3, and 4 with 2 coin of 2. As you can see, this one is from the previous. 2 coin of this one we can 1, 2, 3, and 4. So we can use 1 coin of 2 and 2 coin of 1, 3. But after that, after we move to the coin of 2, we can change it into 2 coin of 2 directly. So this is the smallest, and that's all how it works. until the end. So after that, we can choose the optimal value over here. Let me check. I think it's a little bit different. Well, we can go directly to the knapsack. It's more easier to understand. Okay. Well, in this case, it used 2 dimension, and for me, I use 1 dimension. And what others? Actually, we can write something like this. Base is equal to the memo, this one, or the previous memo. In this case, the memo I will be the highest possible number, the anti-base, and then we write base over here, and we change base over here with base, and then after that we put base and if over here. Like the current memo is the base. Originally something like this, but after that I modify. I modify because I couldn't delete base. So this one. Yeah, I modify. So that's how we get something like this. And after that, at the end, if the memo k is more than 50,000, which means this one, it means that we couldn't find the solution. So we give -1, return -1. But if it gives a solution, it returns the answer. So that's why in here it's the answer will be percentage D, bottom up, and KN here. So this is how I solve the problem normally. You can do something like this similarly. Coin change in C. Not Googling the solution of the problem directly. Well, if you, for example, normally in UVA there are a lot of solution, UVA solution, or just type the problem. As you can see, there are abundant solution. This one solution and this one solution, and this one there is a question and the solution, etc., etc. For example, this one in C++. So if you copy paste this code and run it directly, it should give you the solution. But the most important that you have to understand. That's why it's not recommended way, and it's cheating. So my opinion and my advice for you, because for the programming interview it will be difficult for you. Like try to find the original or the master code of coin change. After that, for example, this one, as you can choose anything. Understand this problem, and I think for this one it use top down. And after that, try to modify so that it can fit with your problem. Maybe it can solve this problem. Sorry. So that's how I did. And okay, there are still, is it complicated for you to understand with this explanation? First, try to find the master code, and then try to modify to adapt with this with your problem. Then profit. You understand the problem and you understand you can do the solution. Do you have any question for this kind? No problem. If you understand this coin change, how it works and how the code works, normally it's not too difficult, or you can reproduce or reuse it again for this one and this one. No question so far? Okay, if there is no question, so we move to the second problem, which is knapsack. So this is similar way. Try to do the similar way. Anda masuki gua yang mengandung K batu mulia. Batu-batu dinomori dengan 1 sampai dengan K. Batu ke I memiliki berat WI kilogram dan harga jual HI rupiah. Anda bawa sebuah tas kapasitas N kilogram. This is the main characteristic of knapsack. There is limited size of sack or bag. And then there is something, other parameter or other features that you have to consider to get optimal. So as you can see over here, this is the price. You have to get the optimal price. Batu-batu harus dimasukkan ke tas ini untuk dibawa keluar. Tentu saja tasnya tidak bisa memuat batu-batu total lebih N kilogram. Sebuah batu juga tidak boleh dipecah dan diambil sebagian saja. So if the stone can be split or can be broken. Actually, this is the problem of fractional knapsack or partial, fractional knapsack. And then we continue. Tentukan batu mana saja yang perlu dibawa supaya total harga jual dari batu yang dibawa maksimal mungkin, optimal mungkin. Then you can try to start to this one. This is the input 11 and 3. So the maximum weight is 11, and there are 3 stones. The first stone, this is the weight, and this is the price. This is the height. This is the price. So the optimal is to bring over here is 2 and 3, which is this one. 2 and 3, 6 and 5, because if we sell it, the total value will be 17 plus 14, which is 31, and it's higher than 30. For the second input, 30 and 4, and this is the price. All what we can do with well, if it fits, it gives the same price. Just bring the smallest, ditambahkan batu dengan nomor yang lebih kecil. Wait, this one, meminimalkan beratnya. You have to consider the minimum weight if the value if the final price will be the same. So how I solve it? Actually, you can just like what I did before. Visit this one, knapsack. Not with the flying table, but this one. So actually the problem is similar. If you open the book, diberikan N sebuah barang, nomor 1 sampai N, harga rupiah, terus kapasitas kilogram. Demikian sehingga jumlah berat barang yang kita masukkan tidak lebih dari kapasitas tas dan jumlah harga yang sebanyak mungkin. But the differences is in here you have to you have to print only the optimal value, which is solusi terbaik mengambil barang 1, 2, dan 5. 1, 2, 5 with the weight 5, 4, and 4, which is 13. The optimal, if we have the maximum weight 14, so we get this one, 1, 2, and 4 to get the optimal value, get the optimal price, which is 6 plus 5 plus 4, 15. So in the easiest way is, well, in this case, in knapsack, is to get the optimal value. In order to do that, you can copy this one. You can modify from this one, or let me show you another sample of sources. I try to find, is there, well, instead of recording by myself, I try to like copy paste and modify it from other people's work, but not the, literally not the problem, solving the problem, but the original of knapsack problem. So this is the differences. You understand the problem and then you understand how to solve it. So the differences in here, it's to find the optimal value While in here, you have to find the optimal solution, as you can see over here. If there is more than one optimal solution, try to find the smallest possible. So, yes, I got this code from this reference. Well, it's in India, Indian guy. So I read his explanation to make sure that it's the same problem as what I'm looking for. Then try to copy paste this one. Then I got this one. As you can see, even I give the similar pattern. Just copy paste the master code of knapsack. After that, I modified to adapt with my problem. Wait, let me, where is the problem? This one. To solve this problem. So it's a little bit different than this one, I think. But in general, it used the same paradigm. For solving with this one, as you can see. For solving, we can use 0 if I equal to 0, this one. Or you can use dp I minus 1, which is this one, I minus 1, w, small w. Or the maximum, we can choose the maximum price. So we compare. This is how I solve the problem or take the similar answer. Yes, this is how I solve the problem and get the similar pattern. Because if, let's say, if you read or if you get the code from here, like transforming the pseudocode to the code, or you get from the internet, in general, they have, well, existing code, it's abundance everywhere, the knapsack. Then the most important is you have to modify. In this case, I have to modify with minimize weight, and then printing the weight. Because if you solve this, if you solve this one, you only get the optimal value, not the optimal solution. Even with this one also, it's the same. You will get the optimal value, not the optimal solution. To prove it, let us run the code. Well, let us try to, let me stop. With the master code first. First, we have, there are 4, or we can try to adopt from here. 11, 10, 30. Well, I start with 0. It means that if the maximal value is 0 and the price is 0, then just print the 0 value. Then 10, 6, 5 as the price. No, it's the weight. And then the price is 30, 17, and 14. So we have we have 3 kind of stones, and the maximal value is 11. Let us run directly. Control S, run it directly, and then this is the representation. That's why it's important to understand the problem or understand how we represent in bottom up, etc. As this guy mentioned over here. So I can print over here just to make it easier to understand. At the beginning, it's 0, so there is no solution. Then it's 30. 30 over here is this one. This one is the weight, and this one is the stone. As you can see, the weight is from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11. And then the stone 1, 0, 1, 2, 3. So if you only know the first stone, for example, the first stone, the weight is 10. That's why the 10, when it arrives at 10 for the weight, we fill it with 30 because the price will be 30, as well as 11. It will be 30 also. But if we know other stone, for example, this one, 6. So at the index of 6, we fill it with 17. 7 also 17, 17, 17 until we reach this one is 30. And then for 11, starting from here, we compare it, which is more efficient or which is more valuable. The stone with the weight of 6 or the stone with the weight of 10. So if we compare, it's more valuable if you consider the stone with the weight of 10, which is 30 compared with 17. So it's still 17. But if we consider the third stone, as you can see, 5. So index at index 5, we fill it with 14, and then we compare it again. 6, we can fill it with 14, but we can also fill it with 17, which is a more valuable 17, 17, until this one, or 30, until at the end this one. So in this one, we compare it. Find the maximum between the previous one is 30 or 17 plus this one. And the price 17 plus 14, which is 31. And then that's how we get the maximum, which is 31, the maximum answer. So we get the optimal cost 31. So that's how we get the optimal value. After that, how we get the selected object? If you read or if you follow this course from this guy, you will find let me copy paste reference so you can understand it better. So you will get recommendation from this guy to fill out or to print the selected object.
Hi, the topic is 01 apps.
Sorry. Actually, he gives wrong answer over here. Wait, let me. Well, this one. This is to compute the optimal selected code, but it's wrong. Actually, the correct answer is he has a little bit wrong, and I mean it's after this one. So put it at the end. So G, small g, equal this one, and then followed by I mean. So by doing this, we get this solution, 3 and 2. But if you submit this source code, for example, you just need to reverse it, or you just need to sort it with certain sorting algorithm, it's easy. But if you print this solution, like this one, you modify it and you submit it, you will get wrong answer. Why? For example, in this case, let me check the submission. Actually, at the end, I got the wrong answer. What happened? I just copy paste and then reverse it, or get the sorted in sequence. Actually, the problem is, and this one I got a correct answer. For example, if we cut until this one, let's say until 17 or 9, the maximum weight is 9. So we get 17, but we have to check whether 17 previous row is 17 also or not. If the previous column, sorry, in the same row, previous column is 17, so we consider the smallest weight. As you can see over here, if this one is 9, and this one is 8, and this one is 8 and 7, sorry, and this one is 6. So after that, this one is smaller. Oh, it means that we achieve the minimal weight with the optimal solution, or with the optimal value obtained from here. So we print this one. 17, 6. So from this current value, how we get 17 and then minus etc. So I think it's Azan. You can try try to understand the code firstly. So try to understand the problem. I try to find possible solution. The another test case that can represent mentioned problem. Let me know if you have any question. Actually, when I tried with the master code from the reference, which is from the YouTube guy, I got the wrong answer, which is 4 and 3. This is wrong. And the correct answer is this one. So I divide it. Given the same circumstance, the same problem, I get 1 and 2, which is the correct answer. And the optimal is 3, the optimal value. As you can see, that's why I got the wrong answer when I submit my first trial, my first code. So, okay, I think that's all for the knapsack. I'll give you, is there any question so far? No? If there is no question, I would like to give you like 20 minutes to solve the problem, to solve the knapsack, or wait. Usually with Mr. Subakti, the course finish at 3:30, right?
Yes, sir.
Yeah, maybe for the next 25 minutes, try to solve the knapsack and submit it to the assignment. Whether you can submit, whether it's accepted or not, just submit it. Never mind. At least you try. Then let me check. Then for the next week, next week is the holiday. That's Idul Fitri. Well, just for your curious, maybe I will not bother to give you the question and the task during the holiday, Idul Fitri. Maybe you are curious to submit this one and we can discuss our next meeting. Okay, thank you. Selamat Hari Raya Idul Fitri bagi yang menjalankan. So I'm waiting for the next submission. So it's 15:30. Good afternoon. Okay, no question so far. There is no question. Okay, thank you very much for your attention. Selamat siang. Semoga senantiasa dijaga kesehatannya. Assalamualaikum warahmatullahi wabarakatuh. Goodbye. See you next meeting.
Thank you so much.